Welcome to the AI Grass Whisperer. It sounds a little out there, I know, but today we're diving into a really cool experiment. We're going to see if we can teach a computer a very human skill, like, can it figure out how much grass is in a field just by looking at a picture? We're going to break down the actual code that tries to pull this off.
So let's get right into it. Think about this for a sec. If you're a farmer, or maybe an ecologist, you absolutely need to know how much plant matter, that's called biomass, is in a field. Now, the traditional way, it's a total pain. You've got to go out there, cut samples, dry them, weigh them. It's slow. So the billion-dollar question is, could an AI just look at a photo and tell you?
And that's exactly what this code notebook we're looking at is all about. It's a digital experiment, and we're going to walk through it step by step to see how you could actually train an AI to become a grass whisperer.
Okay, so here's our first big hurdle, the training. We've got to take a general-purpose AI and turn it into a real specialist, right? Kind of like a digital botanist that can look at a bunch of pixels and somehow understand what's grass and how much of it there is.
And the tool for this job? It's something called a convolutional neural network, or a CNN for short. Now, you can think of a CNN as an artificial brain that's been specifically built for vision. It's a natural at spotting patterns, textures, and shapes in pictures, which, makes it pretty much perfect for what we need. This CNN is our expert in training.
But, and this is a big but, here's the catch. For a CNN to get really good at its job, it needs to see a massive amount of examples. We're talking thousands, sometimes millions of photos. And in the real world, especially when you're doing scientific research, you almost never have that much data. So what do? What happens when your photo library is just too small?
Well, that brings us to the absolute core idea of this whole experiment. We're going to open up the augmentation playbook. This is the secret weapon that lets an AI learn a lot more from a lot less.
So what on earth is data augmentation? It's actually a super clever trick. Instead of going out and taking thousands more photos, you just take the ones you already have and create slightly tweaked copies. You can flip them, rotate them, maybe mess with the brightness and color a little bit. You're basically creating brand new, unique training examples for free. The best way to think about it is like this. Imagine you're teaching a kid what an apple is. You wouldn't just show them one perfect photo, right? No way! You'd show it to them from the side, from the top, maybe in different lighting. Data augmentation does that exact same thing for the AI. It makes the model more robust, less brittle. That means it won't totally freak out if it suddenly sees a photo of grass taken on a cloudy day instead of a sunny one.
Okay, so this is where it gets really interesting. This code doesn't just use augmentation, it runs a full-blown experiment. It actually creates 4 different augmentation recipes, from doing nothing at all to getting super aggressive with the changes, just to see which one works best.
And right here, you can see the setup, pulled straight from the source code. It's laying out the 4 strategies we're about to test. No augmentation, a light version, a medium version, and a strong one. Each one just layers on more and more transformations.
Let's just quickly break down what these levels actually do. Step 1 is our control group, the original photos, totally untouched. Step 2, light, just adds a simple horizontal flip. That's it. Step 3, medium, starts to get a little more creative with flips, rotations, and even some subtle color shifts. And then step 4, strong augmentation, well, it basically throws the kitchen sink at it. We're talking aggressive flips, wild rotations, and even shifting the position of the image around.
Now, what makes this a real, proper experiment is the control. The AI model itself, that CNN we talked about, is exactly the same for all 4 tests. The only thing we're changing is that augmentation recipe. That way we know for sure we're seeing the effect of augmentation and nothing else. It's a fair fight.
All right, before we get to the results, we gotta know how we're keeping score. The metric here is called the weighted R-squared score. Look, all you really need to know is this. It measures how close the AI's guesses are to the real ground truth measurements. A score of 1 would be perfect, so the higher the score, the better the AI is doing. Simple as that.
Okay, the moment of truth. The experiment has been run, the models are trained, it's time to see what happened. Which one of these 4 strategies actually created the smartest digital botanist?
So each model was trained for 20 rounds. They're called epochs in the biz. Let's see how things shook out over the course of that training.
What's really fascinating here isn't just the final score, it's the journey. You can see all 4 strategies battling it out. It's a pretty close race for the top 3, but just look at that blue line for no augmentation. It is all over the place. It hits some impressive peaks, but then it has these catastrophic drops.
It just goes to show that training without any augmentation is super unstable.
And here we go. These are the final numbers, pulled right from the notebook's summary table. This cuts through all the noise from that chart and just gives us the cold, hard facts on performance.
So the verdict is in. If we look at the average performance across all 20 rounds of training, medium augmentation is our clear winner. It gave the most consistent, the most reliable, and the highest performing results overall.
But hang on, there's a really interesting twist in the data. While medium was the best on average, the light augmentation strategy, it actually hit the single highest score of any model in one specific round. And that tells us something important. Sometimes, a simpler approach can have these incredible moments of brilliance, even if a more complex one is more reliable in the long run.
So let's zoom out. What are the big takeaways here? Well, first off, doing any kind of augmentation is way, way better than doing none. That's a slam dunk. Second, there's a definite Goldilocks effect, a sweet spot. Medium beats strong, which proves that if you go too crazy with the transformations, you can actually just confuse the AI and make it worse. And finally, consistency is king. The best strategy wasn't the one with the highest single score, but the one that performed well, reliably, time after time.
And that leaves us with the bigger question, doesn't it? We found the sweet spot for analyzing grass, but what about a totally different problem? Imagine you're training an AI to recognize human faces. Would you want to use strong color changes? Probably not, right? Would you ever want to flip a face upside down? Almost never. It just makes you think. The real art of training an AI isn't just about having more data, it's about having the right kind of data. So what's the perfect recipe for your problem?